There we go. Okay, so now we're into chapter 15 here. And this is essentially buffers. All right. So, further discussion about equilibrium. Say we have the acid reaction or dissociation of acid in water, but that's not the only thing in there. If, say, we have, we're going to have an example in just a minute. Okay, so we've got this equilibrium, this acid equilibrium, and the acid dissociates in water to produce a conjugate acid and a conjugate base. And everything's in equilibrium and settled. Then you do something to disturb it. Now we're invoking Le Chatelier's principle. And if you disturb the reaction by adding some ion that is already found in the reaction, you induce a common ion effect. That in its simplest terms, that's it. So here's an example. Suppose we have this hydrocyanic acid in water, and it dissociates to make some hydronium ions and cyanide ions. What will happen if we add sodium cyanide to this mixture? Look for the common ions. Is there any sodium in here? No. So when you add sodium cyanide, which dissociates into these two ions, which one is going to influence the equilibrium? Only the cyanide, because it's part of the reaction. So when you add sodium cyanide to this solution, what will be the effect on the number of protons in solution? If you add cyanide, it's going to consume some of the protons and shift the reaction to the left until equilibrium is reestablished. So that means cyanide addition of sodium cyanide will remove hydroniums or protons from solution, and the acidity will be decreased. Or another way of saying it is the pH will be increased as a consequence. All right? This is the basic concept of buffered solutions. Buffered solutions, by definition, resist a change in pH. They don't eliminate a change in pH, right? In a buffered solution, if you add a source of hydrogen ions, you will get an increase in pH, but the increase will be very, very small over a certain range of concentrations, right? That's important. Or if you subtract protons or add hydroxyls, add a base, then the pH shift will be very small. That's what we mean by buffered solution. The change in pH is resisted. And we accomplish this by one of two ways. The most common way is to create your buffered solution using a weak acid. In conjugation, in conjunction with the conjugate base of the weak acid. So we would say HCN plus some source of cyanide ions. So we'd have some of this and some of that added together in the mix to produce our buffered solution. Okay? So what happens when you add an acid to this solution? Well, if we write it in such a way, like this, HCN, excuse me, and I'm going to leave out the water for convenience. And it dissociates into protons and cyanide ions. Okay? What happens if you add an acid to this solution? And this is all together. Is proton a common ion? Yes, proton is a common ion to this reaction right here. So if we add protons, what happens to the equilibrium? It shifts this way, correct? It shifts that way, and if this concentration is high enough, these protons will be consumed in that reaction, and by consuming those protons, the pH is stable. Right? When you add protons to this solution, if there's enough of that in the solution, then you get a very minor shift in pH. Right? You'll get some hydrogen ions, but not a lot of them left over. It all depends on the concentration of this and that together. So what happens if you add hydroxyls? If you add base, then that is going to produce water. Right? It's going to consume hydrogen ions to produce water. Why? Because water is the stable form. Right? H2O dissociation is heavily weighted toward the water because of its Kw. So that means all of these are going to essentially consume enough to neutralize all of these and make water. So at first you may think, well, if we're moving a lot of these, then the pH is going to get higher because you're reducing the number of these. But what happens? You've disturbed the equilibrium. This is going to dissociate if it's there in sufficient quantity and produce more of these to replace those. So again, you get a stable pH. So addition of acid, addition of base, doesn't matter. The pH is going to be relatively stable as long as you have sufficient numbers of these and these in that solution. That's the key. What's the concentration of that and that in solution? All right. Okay, let's see. This slide might be out of order because when we start talking about ratios of the acid to its conjugate base, now we're getting to the point where we need to discuss a new manipulation of the equilibrium expression. So what would the equilibrium expression be for this one? Right? K is equal to this one times that one over this one. So if you want to protect movement of pH with this expression, what would you want to do? You would want to find some concentration where you could maximize that and that at the same time. If you had very little of this, then it would not respond to acid addition the same way. If you had a very little of this, then it wouldn't respond to base addition. So the best compromise is equal amounts. Have the same amount of this as that. Then, if you add acid, you've got enough of this to consume the protons and reestablish equilibrium. Or if you got this and you add base, you've got enough of that to dissociate and reestablish the equilibrium. So the ratio of HA to A minus, in that case, in this case, this ratio here needs to be 1, equal amounts. Okay, that brings me to the discussion of Henderson-Hasselbach. So what did Henderson-Hasselbach do? Let me see. Okay, I do have a discussion of that. So there's your generic acid equation. There's the Ka for that expression. And if you rearrange it, you can determine the hydrogen ion concentration if you know the K for that reaction and you know the ratio of HA to A minus. Right? You could either know the absolute concentrations of each one, or if by some other means you determine the ratio. By the way, if they were 1-to-1, if they were half of it was this and half of it was that, then this would be 1, and 1 times Ka means that the hydrogen ion concentration would be equal to Ka. Right? Okay. So, Lawrence Joseph Henderson published this equation, his equation, and we haven't derived it yet, so hold on just a second. Published his equation in 1908. 1909, Sorensen published his pH system. He proposed the system. Right? Then Hasselbalch took Sorensen's pH proposal and applied that log transformation to Henderson's equation. So this is Henderson's equation here. Hasselbalch came along and applied Sorensen to that equation, which means what? Negative log of both sides of the equation. So here's the way it looks. We've got Henderson's equation. We say negative log on this side, negative log on this side. There you go. Negative log there on that side, negative log on this side. Right? So when you take the log of a product, then you add the log transformations. So the log of this one plus the log of that expression. Now, why do we keep this one separate? Why don't we say log of HA minus log of A minus? Because we're more interested in the ratio, not the absolute amounts. And that's the way Hasselbalch approached the problem. So when you reduce that, you get pH here, obviously, pKa here, and we leave this one alone. Negative log of HA over A minus, except we don't like negatives that much. It's too easy to make a mistake. So what transformation will give you a positive sign here? Well, the log of A over B is equal to negative log of B over A. Right? So if we invert this expression, that changes the sign to a positive. That's the Henderson-Hasselbach equation. So both of the men were given credit because Henderson proposed this form, then Hasselbalch used Sorensen's transformation to produce this form, and now this is the one that we use. So what does this mean? That means if you know the ratio of the acid in the denominator to the conjugate base in the numerator in your solution at equilibrium, and you know the pK for the acid, this one right here, then you can calculate the pH of that solution. What does that mean? That means that for all solutions of this acid chemistry, weak acid chemistry, the ratio of conjugate base to acid is the important number. The ratio, whatever the ratio is, if it's concentrated or weak, that is high concentration, low concentration, as long as the ratio is the same for any of those solutions, the pH will be the same. Okay, so if you want to maintain a pH very close to its buffer pH, for the addition of lots of acid or lots of base, then you want these absolute values to be high, but their ratios to be the same for all other possible combinations. So what are the hazards of that? Well, in chemical systems, the hazards are not that big a deal. For living systems, when you want a buffered pH solution for living systems like cell culture or preservation of tissue, then you also have to consider not just the pH, but the ionic strength. And if you put a lot of this conjugate base in there or a lot of this acid in there, then you run the risk of damaging the tissue, not based on pH, based on ionic strength. Right? So that has to be a consideration in proposing a buffer solution for a living system. That could disrupt membranes, right, for cells. The other possibility is enzyme systems. Remember, enzymes are biological catalysts, are very sensitive not only to pH, where the buffering effect is important, but they're also sensitive to ionic strength in the solution, because almost all enzymes are proteins. And if you increase the ionic strength of a solution too high, it will denature the protein. It will break up its structure, and its activity is dependent upon the structure. It's three-dimensional arrangement, right? So you have to be careful there. For simple enzyme systems, I mean, if you're doing an experiment in vitro, that is without cells, then you would also have to consider the ionic strength. So you can increase these concentrations only to a certain level before you disrupt your enzymes. Okay. So what's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? Now, I assume that under these circumstances, this is equilibrium concentration. The Ka for acetic acid is 1.8 times 10 to the minus 5. So what is the concentration of the acid? 0.45 molar. That's HA in our equation. There you go. So the acetic acid concentration, 0.45, goes down here. And the conjugate base concentration, 0.85, goes down here, because if the sodium acetate is 0.85 molar, for each mole of sodium acetate, you get 1 mole of acetate ion. So the concentration of acetate is the same as the sodium acetate. Goes there. And the pKa is what? It's not 1.8 times 10 to the minus 5. It's the negative log of 1.8 times 10 to the minus 5. Right? That goes in here. Then if you do that calculation, right, just like this, you find that the pH of the solution is 5.02. So this is just an illustration. If this is your buffer, then you add hydrogen ions, and they combine with the conjugate base to produce this effect. And then the system responds to replace the A minuses. Or if you add base, you're essentially consuming HA, because you're taking the protons out, and the HA shifts toward the proton side. And then the equilibrium also shifts to replace those protons. Okay. That's the most common type of buffering recipe. It's made with weak acids and their conjugate bases. All right. That doesn't mean that you can't form a buffering solution with a weak base and its conjugate acid. For instance, ammonia. Right? If you did it with ammonia, then you would produce, let's see, we need water in there, don't we? Plus water. Then you would produce ammonium plus OH minus. If you add acid, the hydroxyl consumes it, because hydroxyl is a very strong base because it comes from a weak acid, water. And if you add hydroxyls, they consume this one. They extract protons here. And then the reaction shifts that way to replace them. Okay? So you can form a buffer out of weak base also. It's just more common to use weak acids. All right, so let's get back to the discussion here. So the pH in the buffered solution is determined by the ratio of the, and we're going to stick with weak acids for now, is the ratio of the conjugate base to the undissociated weak acid. And this will be preserved, the buffering capacity and the effect of the buffering solution will be preserved as long as the addition of acid or base is small compared to the concentration of the conjugate base and the weak acid. It can be overwhelmed, in which case you exceed the buffer capacity. Oh, good. I do have a diagram coming up. So this buffer capacity is measured as the amount of proton or hydroxide that a buffer can absorb without a significant change in pH. And that's determined by how much of the weak acid and the conjugate base are in solution. The optimal buffering capacity is where you have equal amounts of HA and A minus. That way, you have the maximum available amount based on your equilibrium expression. You have the maximum amount allowable. Half of it is this, half of it is that. That guarantees that you will be ready for the addition of acid or base. So this quantifies the buffering capacity, and you don't have to know this. It's given a Greek letter beta, right? And it's the change in N divided by the change in pH. So change in the addition, the change in normality of the added acid or base for a change in pH. It's just that ratio. And the normality is used because if you add a polyprotic acid, then the normality takes that out of the picture. Normality is an expression that equalizes rather than molarity. Normality says will convert diatomic, diprotic and triprotic acids into a form that is equivalent, all acids equivalent. But you don't have to remember this. This is just for illustrative purposes. I'm not going to give you any problems that use this calculation. Okay. So where is that pH? The buffer, the center of the buffer pH range. It occurs when the pH is equal to the pKa. Right? Remember the equation. Right? If that is equal to that, then that ratio is 1. And what's the log of 1? The log of 1 is 0 because it's 10 to what power equals 1? A number to 0 is always 1. So that means this becomes 0 when that one equals that one. Okay? So now that means that at that ratio, pH is equal to pKa. So if you know the pKa of the acid, you can predict that is the center of the buffer range, the pH buffer range. Okay, so let's do a titration. Right? You know what a titration is? A titration is the addition of one solution to another one with the measurement, incrementally measuring the changes that occur. So a pH titration is one where you measure the change in pH as you add an acid to a base or a base to an acid. In this case, we're going to add base to our acid because the acid is the weak part. So we're going to start off with the acid and gradually add more base to it. So you eventually reach a point where the amount of base is equal to the amount of acid in solution. And at that point, the stoichiometric equivalence point we call the equivalence point. All right? And this is what it looks like. As you add, right, you start off with your acid at a low pH down here, right? And in this case, we have nitric acid. That's not a weak acid. So this is, we're starting off with strong acid, strong base titration. So if you start off with nitric acid at a very low pH, and you start adding base to it, then you gradually get an increase in pH. And at a certain point here, which in mathematical terms is called the point of inflection. Notice that this part of the curve is concave up, and this part of the curve is concave down. The point at which that changes from up to down, right here, is the point of inflection. And on that curve, that is the equivalence point. For a strong acid and a strong base, that equivalence point always occurs at pH 7. Right? Strong acid, strong base together means a neutral solution. Right? So that's what that titration looks like. You can do the same thing if you start off with acid and add base to it. I mean base and then add acid to it. So the base, you're going to start off up here. And then you add acid and you reach an equivalence point at 7. And there you go. All right. Pardon me for just a second. I'm being paged. All right, I'm back. Okay, so we've got this titration in mind. And if we start off with an acid and add base to it, pH goes from acidic on up toward basic. And it follows that sigmoid curve. Right? Sigmoid meaning S-shaped. Now, what does the titration curve look like if we use a weak acid and a strong base? Well, it also produces a point of inflection where you have an equivalence, but it occurs at a different pH, not at 7, right? Remember, weak acid, strong base, they're equivalent at a basic pH. So when you titrate a weak acid and a strong base, that inflection point, the equivalence point, occurs at a pH greater than 7. All right. So, all right, it's not in the, okay, hold that slide for a second. If we titrate, and this is added sodium hydroxide, and this is pH, and the acid is acetic acid, right? Vinegar. Then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then we add incremental sodium hydroxide. The starting point, when there's no base added, is going to be in the neighborhood of 3.5, right here. So that's where we start. Initially, when you add base, the pH is going to jump up. It's going to do like this. Right? But then, by the way, what is happening? The reaction says you're going to have HC2H3O2, 2, and it's going to dissociate into like that, and C2H3O2 minus acetate right there. So what's happening? As you add base, it's not the sodium, it's the hydroxyls. the hydroxyls are combining here to produce water. But the shift, since we're removing hydrogen ions, the shift is this way, producing more acetate ions. All right? So by doing this titration, we're starting to build up a higher concentration of conjugate base. So you can see where this is headed. As we gradually add more base, we get to a point where the curve flattens out. So this pH is maintained as long as the ratio of these two is within a certain ratio, concentration. Right? Remember the A minus over the HA. And then at a certain point, you've added so much base that there's not much of that left, right? It cannot sustain that equilibrium anymore. At that point, the pH now responds to the addition of the hydroxyls, and it goes like that. And then you reach a point right here. That's the equivalence point. So the number of moles of base, right, moles of base now equals moles of acid at this point. And then you keep going up until you reach a point where the pH doesn't change anymore. It just flattens out like that. Somewhere in the neighborhood of 12. Okay, so that's the general sigmoid curve. And notice that this inflection point is up here in this neighborhood. It's not down around 7. Okay, so what does this mean? This means that in this case, at the equivalence point, you have used up all of the hydrogen ions. So at what point then would you have half of the hydrogen ions still available? And consequently, these two would be equal. Right there, right? 1/2 equivalence. So at 1/2 equivalence, now we have this ratio, C2H3O2 minus divided by HC2H3O2. That's equal to 1. That's why this is the ideal buffer pH for any weak acid. And the pH range for the buffer is right here, like that. Okay. We use this type of titration in my general chemistry class to determine the Ka value for, experimentally, the Ka value for acetic acid. You just do a titration, right? And you find out this curve, you find out half over here like that. So what is this right here? If these two are equal, then the pH is equal to the pKa. So at this point, that pH is your pKa. And then if you want to find the Ka, you just use the antilog of the negative, and you can find the Ka for acetic acid. Okay, so let me get back to my slides. So when you have a weak acid and a strong base titration, you need to break it up into two separate problems. First, approach it as a stoichiometry problem, in which case you have consumed all of the acid and made that base. So at that point, depending, it's not consumed all of it, but at whatever point you're given, how much of the acid was consumed. And then use that as your starting point for the equilibrium. Then at that new point, that new location, your ICE, the I point after the stoichiometry, that becomes your I point. And then you say the change and the equilibrium from that point, then you can calculate the pH from there. Now, that's in a case where the reaction mechanism, the reaction equation, is more complicated than just a simple acid reaction. If it's a simple acid reaction and you're given values for these and these, then you can use Henderson-Hasselbach, and it'll give you exactly the same result as using this two-step process. So let's do one of those. Let's do one of those as a practice and compare it to Henderson-Hasselbach. All right, so let's consider this situation. 0.1 mole of hydrocyanic acid is reacted with 0.04 mole of sodium hydroxide in 1 liter of solution, which means 0.1 molar, 0.04 molar. First of all, what are the major species immediately upon mixing? That is, before any reaction occurs. HCN, because it's a weak acid, sodium and hydroxide, because that's a strong base, and water. So what reactions result from that? Well, of course, you've got the water reaction, and you've got the HCN dissociation. Then you can have hydroxyl plus HCN, right, producing this. Sodium and hydroxide will not react because they're completely dissociated. And sodium and water will not react, right? So we cancel those two out. Now we compare these three reactions. How do we decide which one? Well, we look at the equilibrium constants for each one. Notice that this one is the Ka for hydrocyanic acid, and this one would be the reverse of the Kb, right? If you flip that around, that would be the Kb, right? Cyanide ion plus water. We would need to use the reverse of that reaction, the inverse. Let's see. Well, the reaction that's occurring, let me back up. We know which reaction is occurring first. It's this one, hydrocyanic acid plus hydroxyl, because that is the titration. So we did need to focus on that one. And we focus on that one as the stoichiometry part of the problem, right? So in that case, oh, we're not going into depth with this one? Okay, my mistake. I thought we were going to dig into it a little more. But it looks like we're going to look at this reaction, acetic acid. So we have 0.03 moles of sodium hydroxide in 1 liter and 0.2 moles of acetic acid. So it's 0.2 molar, 0.03 molar. Major species, there you go. We eliminate those two. They don't make any sense. Then we compare the K values. For this reaction, it's 10 to the minus 14. For this reaction, right, it's 10 to the minus 5. For this reaction, the KB for that reaction, in fact, that is reversed. The KB should be this as reactants and this as product. So what does that mean? That means if this is very small, then this reaction should be, actually that reaction is not dominant. So the stoichiometry, okay, excuse me, this is a two-part, pardon me. So the first reaction that occurs is this stoichiometry reaction. So we have this one combined with the hydroxyls, and this is the initial concentration, there, that's 0. So we know the reaction's going to the right. So this is subtracted amount. For the stoichiometry, all of the hydroxyl is used up. So this is part 1. So this is the part 1 reaction where we're actually doing the titration. So we're using up all the hydroxyl and also consuming acetic acid in the process. So now at equilibrium, actually this is not equilibrium. This is at endpoint or equivalence. This is at equivalence. That's equilibrium is a bad term there. Equivalence, you have 0.17 molar left of this, none of that, and some of this. Now we go to the equilibrium expression, right? We go to this one. And we put in our equilibrium values, our equivalence values, 0.17 molar here, 0.03 molar there. And this is 0. So we know the reaction's going to the right. So we set up our equilibrium to reestablish equilibrium from the position of stoichiometric equivalence. And there's the expression, there's the K for that reaction, right? That's acetic acid. And we determine that the hydrogen ion concentration is this value, and the pH is that value. Right? So what if we use Henderson-Hasselbach? Okay, we know now that based on the stoichiometry, that 0.03 molar conjugate base and 0.17 molar acid left over, plug it into this equation, and the pKa, remember, is the negative log of the Ka, so that's that value, gives us a pH of 3.99 under these circumstances, same as before. All you have to do is determine what is your equivalence point. Right, there's the equivalence point, then you can plug that into the equation and gives you the pH. So that's a lot easier to do than all this other math. So we're going to use we'll use the ice table in the standard procedure first. For this situation, 100 milliliter solution of 0.1 molar acetic acid. What's the pH of that solution? Oh, this is, okay. We're not doing a titration here. We're just determining the pH of that solution. Okay, so there you go. We just run through the ice table as usual with this equation as our guide, and we end up with a 2.87 pH. So what if we take that 100 milliliters of 0.1 molar acetic acid, right? 100 milliliters, 0.1 molar acetic acid. Now, and add 50 milliliters of 0.1 molar sodium hydroxide. Okay. What happens first? The reaction, we let the reaction go to completion. So that means all the hydroxyls are used up, some of the acetic acid is used, and produces acetate, or the conjugate base. So now we're not at equilibrium, we're at equivalence. I need to correct that too. Then you take those values and you put them, right, take that the same ice table, and now you take this value here and this value here and put it in the Henderson-Hasselbach, and you can calculate the pH at 4.73. So how do we know the molarity? Look at this. I thought the molarity was 0.1 molar. No, it's not. The molarity is the moles divided by the total volume. Now the total volume is not 100 mils, but 150 milliliters. So you need to find out how many moles. 0.1 times 0.1 is 0.01. And then you have 50 milliliters of 0.1 there. That's for the base. And if you calculate the molarity based on the new volume, then these are the values you get. Right? It's all based on concentration. All right. So I made that point. Let's see. Where am I going from here? Okay. So let's say we make a solution of 100 milliliters of 0.1 molar solution of ammonia, which has a Kb of 1.8 times 10 to the minus 5. Wow, that Kb is the same as the Ka for acetic acid. And you combine with that 50 milliliters of ammonium chloride. So this is not a titration. This is actually mixing a buffer. So you've got the base, and the conjugate acid here is ammonium ion. Okay, so how do we approach that? Well, what's the reaction that we're interested in? Well, we have ammonia plus water yields ammonium plus OH minus. The initial concentration now has to be recalculated because we have a 150 milliliters, not 100. Right, so you do that same calculation for ammonium and ammonia. So that's our starting point. No hydroxyls, that means the reaction's moving toward products. We're losing some here, we're gaining some there in equivalent amounts. This is your equilibrium concentration on each side. So what's the controlling reaction here? This is a Kb expression. So we have, let's see. Yes, the Kb expression, actually it doesn't show you. The Kb expression puts ammonium concentration times hydroxyls divided by ammonia. So that's what this is here. And we calculate the OH, the POH, and the pH. And we can determine that it's 9.56 pH using the long version. How would we use Henderson-Hasselbach with a base? Right? We know how to do it with an acid. What we have to determine is what is the ratio of acid to conjugate base. So what's the acid? The acid is ammonium, and the base is ammonia. So those are the concentrations that we determined from the previous reaction. Now we have to know the Ka, because Henderson-Hasselbach doesn't deal with Kb, it deals with Ka. So we use our Ka calculation to convert Kb to Ka. Now this is the Ka value. and we put that Ka, well, the pKa here. Hold on a second. Okay, we skipped a few steps. What we're saying is, with that Ka introduced into the equation, Henderson-Hasselbach equation, here. And for this one, we would have the base over the acid. There we go. That's the way you would express it for Henderson-Hasselbach. You need to know the pKa. Well, what we're saying here is, you know, that's not. Oh, okay. I didn't finish. Pardon me. We need to know the pKa. Right? So the pKa is 9.25. Now we can put that into the equation. 9.25 goes here. Then you have the log of those other two values, 0.0667 divided by 0.0333 equals the pH. And it turns out to be 9.56. Right? So in order to do a base buffer, it takes a little bit more work because you have to calculate the Ka before you can use Henderson-Hasselbach. But it does work. All right. So if we approach this problem, we're asked to calculate the pH of a solution made by mixing 1 liter of a 0.5 molar solution of ammonia which has a Kb of 10 to the minus 5, and a half a liter of 0.1 molar ammonium chloride. Notice that there's your base and there's your acid. The chloride is a spectator. Then, what's the pH when you add 0.1 molar HCl? So the conditions before, ammonia is 0.5 moles is what you have. Ammonium is 0.1 moles. Right. Now, in this case, we're modifying just a little bit to do the stoichiometry. We know what we're starting out here. Right? So we're going to do the stoichiometry with absolute amounts first, and then recalculate the concentrations before we do the equilibrium half. So 0.5 moles here plus 0.1 moles of acid, right? Here's 0.1 moles of acid right there. Okay? And you start off with 0.1 mole of ammonium. So these are our starting conditions in absolute amounts. And then after the reaction, and we're letting it go to completion, we're consuming all this hydrogen ion. And in the process, we're having to use 0.1 mole of ammonia to react with the hydrogen. So now, after the reaction, we have taken this 0.1 mole and converted it into ammonium. We don't put the change in here, just after the reaction, you've added another 0.1 mole of ammonium here. So now this is our starting point for the equilibrium right here. But we have to calculate concentration before we can do that. So here we go. This is the starting point for equilibrium, right? 1.5 liters now with that many moles. And this is our base concentration. This is our acid concentration. Now, of course, we need the pKa, and we can now put it into the Henderson-Hasselbach equation because we know the concentrations at this point, and we calculate the pH at 9.55, right? When we add 0.1 mole of HCl to this mixture, that's what happens to the pH, right there. All right, we're almost there. So we have another problem. What's the pH of a solution at the equivalence point when 100 milliliters of 0.1 molar solution of acetic acid is titrated with a 0.1 molar sodium hydroxide solution? In order to, and the nice thing about this reaction is, if we have 100 milliliters of 0.1 molar acetic acid, okay, that's given. What happens at the equivalence point? At the equivalence point, the amount of base, 0.1 molar sodium hydroxide, right? Equal concentrations means equal volumes have to be added. That's the only way you can reach equivalence. If both concentrations are the same, the volumes have to be the same. So that's what we're shooting for. That's why the total volume is 200 milliliters or 0.2 liters. So before the reaction occurs, we have 0.1 mole, right? Hold on a second. 100 milliliters of 0.1 molar. That should be 0.01 moles. Shouldn't it? Yeah, that should be 0.01 moles because volume times molarity equals number of moles. So 0.1 times 0.1 is 0.01. So that's the right amount of volume, but this should be 0.01. So there's another problem. Okay, I'll have to fix that. Let's see, where is it? Back here. Here we go. So this should be 0.01 moles. Okay. Of acid divided by 0.2. So that would be, yeah, that would be, okay, this is the right value here, 0.05 molar. But this is the wrong number that gives you that value, I think. 0.1 divided by 0.2. 0.1 here, 0.2. Yeah, that's only 0.5. So the rest of the calculation should be good because that is correct, but this is wrong. That should be 0.01. Okay, so let's go ahead. Now that we know that this is the right value for concentration, initially we're going to have 0.05 molar acetic acid and 0.05 molar hydroxyl. And we're not going to have any conjugate base, excuse me. But they're going to be used up in the process, right? Because they're equivalent. That's the whole point. We're at the equivalence point. So we use up both of them, and we end up with this much acetate ion, right? So that's the beginning for our equilibrium expression. So for our equilibrium expression, we're going to take this acetate ion and react it with water. Right now we've got the equilibrium is actually a conjugate base reacting with water. So we start off with that one. The change is going to be subtract some of this and make some of those. And there's our expression. We need the Kb because this is a base reaction. There's a conjugate base with water. So we have to have the Kb. So we convert the Ka into Kb. Then we can set up the equilibrium expression here and calculate the X, find out the POH, right, because that's OH, and then calculate the pH. So for this titration, the equivalence point occurs at 8.72 pH, above 7. Okay? Now, for various weak acids, we can do titrations. And you'll see that the profile for the titration curve will give you a buffer zone at different levels. For a Ka of 10 to the minus 2, the buffer pH is going to be pKa, which is 2 right here. If the Ka is 10 to the minus 4, the buffer pH, the best buffer pH is going to be pKa 4. And so forth. 6 will be at 6, 10 to the minus 8 will be at 8, 10 to the minus 10 will be at 10. I'm not going to do this one. I'm already way, way, way over. But I will mention one thing. Let's see. I had a thought. Let me back up. Before we get to indicators, let me say a word about titration curves for polyprotic acids. Right? So if the pH is here and the base added here, then for a polyprotic acid, you're going to get a curve that'll show you buffer zones for 2 or 3 hydrogen dissociations, proton dissociations. So for something like this, a triprotic, you're going to start off down here somewhere. It's going to go like this, and it's going to go like that, and it's going to flatten out again, and it's going to go like that, and it's going to flatten out again, and it's going to go like that, like that. So you got first proton here, pKa1, pKa2, pKa3. So with polyprotic acids, weak acids, like this one, you have the potential for creating a buffer at 3 different pH values. You can either do one here, one there, or one there. What you do is choose the correct ratio of weak acid to conjugate base. So for this one, the weak acid is H3PO4. The conjugate base is H2PO4 minus. There you go. For this one, it's going to be H2PO4 minus and HPO4 2 minus. That's the ratio for that one. For this one, it's going to be PO4 2 minus and PO4 3 minus. And that's what you have to consider if you're forming a buffer with phosphate at these different levels, depending on which pH you need to stabilize, either a high one, middle one, or a low one. Okay, so now we can move on to indicators, acid-base indicators. If you're doing a titration, you can do the titration, and you can measure the equivalence point. For this one, it would be, well, for the entire acid, it would be out here. But for a single protic acid, you would have something like this, like that, that, and there would be your equivalence point. If you've only got one titration to do, then go ahead and do it that way. But if you've got 100 titrations to do on the same chemical reaction, you don't want to have to go through this mess every time. So what we do is we select the addition of some compound that itself undergoes acid-base reaction. And when it's deficient in protons, it'll be over here at this color. And when you add enough protons to make it, actually you're starting off with the protonated version. So if you have protons here and you add base, then at some point you're going to remove enough protons from this. Let's do it like that. Protons. You're going to end up over here with a different color for the indicator. This will be deprotonated and this will be protonated. So as you add base, it's also extracting protons from this color. Well, the color change is so vivid by your choice that you don't need much of this, just a very, very tiny amount. So you're actually doing two titrations. You're titrating the main curve and you're titrating the indicator. So after you reach a point and the color changes somewhere in here. And usually it changes close enough in proximity that you can say, at this volume added, right, we're at the equivalence point. Only because you're not using a pH meter, you cannot say that it's the equivalence point. So you have to call it endpoint. So if you choose your indicator correctly, the color change will occur very near the equivalence point. Your endpoint will be almost a match for your equivalence point. And at that point, you can say, this is how much volume was added. Then you can do your calculations. And with a color change like that, you can do 100 in a couple of hours. Okay, so here's an example, right? Here's your indicator, it's protonated, and it dissociates to this point, right? It's a weak acid, and the Ka for that indicator is a value, and this is the expression that mimics that equation. And the pKa for that is 9.4. So if you have a proton here, in this case, the indicator is colorless. In fact, this indicator is phenolphthalein, a very commonly used indicator in student laboratories. If you add enough base and you extract these protons, right, tie them up with your base, then that shifts the equilibrium to the right, and at a certain point, there's enough pink here that you visually can detect it. So it's not just a chemical process, but it's physiological. When can you detect the color change? All right. So that's what's happening with your indicator. It's a concurrent acid-base reaction. So the human eye can detect a difference in concentration based on this color change of about 10 to 1. So the log of a 10 to 1 ratio is plus or minus 1 pH unit, or pKa. So within pKa plus or minus 1, you should be able to do a decent titration with a color indicator. So for phenolphthalein, where the pKa is 9.4, the range of your color change is between 8.4 and 10.4. That seems like a lot, but the pH is changing very fast in here. It's going from here to here with just one drop. So that means that you're going to see that color change with the smallest available increment in the size of your drop. All right. So this is the calculation that justifies that plus or minus 1 pH. Right? So if your pH is either plus or minus 1 here, you will be able to detect the difference in pH. So you try to match the pH of your equivalence point to the pKa of your indicator. So here's a whole list of them, right? It's kind of small, but most textbooks have one of these charts in them. You can go look at them in detail. Notice that phenolphthalein is where? Pink and clear, pink and clear. Phenolphthalein, here it is. Phenolphthalein, right here. Right? Notice that right around 9.49, right in there, is the middle of that pH change. So we determined that the color change for that previous reaction, and what was it? It was 8. Let's see, where was that? .72 for acetic acid at the endpoint. So 8.72 puts it right about here. Right? So that would be a good choice, right? 8.5 to 10.5, I think. You would be able to detect that change and get a fairly accurate determination of the endpoint volume of base added. So you pick your indicator based upon the pH at endpoint. So the pH at endpoint is not the same as the pKa of the weak acid, right? The pKa for acetic acid is in the neighborhood of 4.5, right? You need to determine what is the pH at endpoint. And then you can pick your indicator accordingly.